Good afternoon, everyone. I'm from the Aerospace Information Research Institute in China. Today, I will be presenting on the topic of my report, high-pressure silicon resonant microsensor based on microbeam areas. And then I will introduce my project from 4 aspects: project introduction, design and simulation, fabrication and testing, and conclusion. First of all, high pressure range sensors are in demand across many fabs. We can see chemical industrial. High pressure pipelines often requires 40 megapascal. In marine exploration, deep sea exploration at depths of 7,000 meters face pressure exceeding 70 megapascal. Metrology instruments demand even higher levels of accuracy. In oil drilling, sensors are subjected to pressure of around 200 megapascal in environments reaching up to 200 centigrade. Therefore, maintaining high measurement accuracy under high pressure is a challenging task. We can see that in traditional pressure sensor, piezoresistive sensors are simple and strong enough, but they suffer from poor accuracy due to their high temperature coefficient. Capacitive sensors offer great sensitivity, but they are highly susceptible to environment interference. Resonant sensors, although providing excellent accuracy, but lack sufficient structural strength. In traditional resonant pressure sensors, the basic principle is to sense pressure. So the pressure-sensitive diaphragm, the natural frequency of the resonant beam changes with the pressure. However, the strength of the diaphragm structure limits the sensor's ability to operate in higher pressure range. In our previous work, we try to extend the range. By reducing the size of the diaphragm and optimize diaphragm shape. But the maximum pressure we achieved was only 15 megapascal. We then adopt a new pressure-sensitive approach, utilizing value comprehension to sense pressure. This method was first application in piezoresistive sensors and can withstand pressure of up to 200 megapascal. Yokogawa also adopt value comprehension sensing. They use the diffusion method to control the actual stress of the resonator, achieving a pressure resistance of 100 megapascal. Building on this, we achieved precise measurement at 100 megapascal by using a composite pressure-sensitive diaphragm based on value comprehension. In this paper, we propose another approach for value comprehension sensing, using a microbeam area to control the actual stress. By modifying the pressure sensor at an angle, the actual stress of the two resonators become opposite. Moreover, since the positive actual stress under value comprehension is relatively small, so we introduced microbeams to amplify the axial stress, allowing the values to match. Here, we present the impact of the resonator structural parameters on pressure sensitive from our simulation. We can see that the angle and the number of microbeams have the greatest influence. Afterward, we choose the final structural parameters to ensure high sensitivity while optimizing the design for easier fabrication. And then this is the simulation results showing the relationship between the axial stress of our resonators and the pressure sensitive. We can also say that the pressure sensitivity of the resonator is narrowly related to the axial stress of the resonator. Next is the fabrication section, which mainly consists of 3 parts: cover plate fabrication, SOI agent, and bonding. And on the right side is the packaging for electrical and pressure testing. We build a flowing testing system. On the left is the open loop testing system, which analyze signal using network analysis. While on the right is the closed loop system, where a PC program is used to calibrate and validate the sensor. The open loop test results are shown on the right. Both types of resonators have a Q factor greater than 20,000 within the temperature range of negative 20 centigrade to 60 centigrade, which is promising for the performance of the resonant sensors. Then there is the response of the sensor to pressure at different temperatures. This is resonator 1, and this is resonator 2. Both maintain excellent narrative and temperature coefficients. In the temperature range of negative 20 to 60 degrees Celsius, and the pressure range of 5 megapascal, we can achieve low temperature coefficients less than 1 Hz per degree Celsius. High precision measurement occurs better than 0.02% per scale. Very high quality factor, 20,000. And we get pressure sensitivity matching and high pressure resistance. In our latest experiment, we achieved pressure testing above 200 megapascal using the new package. So this sensor, it has the capability to measure in higher pressure ranges. However, we need to establish a new system for testing and calibration. That's all. Thanks for listening.